Welcome to G Fun Facts Online. Today, we're diving into a topic that sounds like it's pulled straight from science fiction, but is rapidly becoming science fact. We're talking about the convergence of two of the most powerful technologies ever conceived: artificial intelligence and quantum computing. When these two fields meet, they create something entirely new, a synergy called quantum AI. This isn't just about making our computers a little faster. It's about creating a fundamentally new way to solve problems that are currently impossible for even the most powerful supercomputers on Earth. Let's explore this new frontier. To understand the power of their union, we first need to quickly look at the two pillars themselves. First, artificial intelligence, or AI. At its heart, AI is about creating machines that can perform tasks requiring human intelligence, like learning, reasoning, and adapting. The engine behind modern AI is machine learning. Instead of being programmed with rigid instructions, machine learning algorithms learn from data. The more data they see, the better they get. You see this every day in your spam filter, your streaming recommendations, and your GPS. A powerful subset of this is deep learning, which uses artificial neural networks with many layers, inspired by the structure of the human brain. These deep networks are incredibly good at finding complex patterns, which is why they excel at things like recognizing your face to unlock your phone or understanding your voice commands. Another flavor is reinforcement learning, where an AI agent learns through trial and error, like a dog learning a new trick. It gets rewarded for good actions and penalized for bad ones, eventually figuring out the best strategy to win a complex game or control a robot. But all of this incredible AI runs on classical computers, which use bits, simple switches that are either a 0 or a 1. This binary system is powerful, but it hits a wall with problems of truly astronomical complexity. And that's where our second pillar comes in: quantum computing. This is where things get weird and wonderful. Quantum computers don't use bits, they use quantum bits, or qubits. And qubits operate under the mind-bending rules of quantum mechanics. The first rule is superposition. While a classical bit must be either a 0 or a 1, a qubit can be both a 0 and a 1 at the same time. Think of it like a spinning coin, until it lands. It's not heads or tails, but a combination of both possibilities. This allows quantum computers to explore a vast number of potential solutions simultaneously. A mere 64 qubits can represent over 18 quintillion states at once, a number larger than all the grains of sand on Earth. The second bizarre rule is entanglement, what Einstein called spooky action at a distance. When two qubits are entangled, their fates are linked. No matter how far apart they are, if you measure one, you instantly know the state of the other. This profound connection is a key resource that allows for computations that are impossible in the classical world. These principles give quantum computers an almost unfair advantage for specific types of problems, like simulating molecules or breaking complex codes, tasks that would take a classical supercomputer billions of years. However, qubits are incredibly fragile. The slightest vibration or temperature change can make them lose their quantum properties in a process called decoherence, leading to errors. Now, let's get to the main event. What happens when these two titans merge? The synergy is a two-way street. First, let's look at how quantum computing can supercharge AI. This field is called quantum machine learning. The core idea is to use the unique properties of quantum computers to process data in revolutionary new ways. Many AI tasks, especially in deep learning, involve massive mathematical calculations on huge matrices. For classical computers, this is slow and energy-intensive. But quantum algorithms are naturally good at this kind of math. They could potentially speed up the training of AI models exponentially, allowing us to build AIs on datasets of a size and complexity we can't even dream of today. Beyond just speed, researchers are building entirely new types of neural networks based on quantum principles. These quantum neural networks, or QNNs, use qubits as their neurons. By leveraging superposition and entanglement, QNNs could be far more powerful and efficient than classical networks, able to uncover patterns in data that are completely invisible to today's AI. Many AI problems are also optimization problems, finding the best possible solution out of countless options. Think of optimizing a global supply chain or finding the perfect investment portfolio. Quantum computers are natural optimization machines. By exploring the entire landscape of possible solutions at once, they can find the optimal answer to problems that would stump classical computers for millennia. But this relationship isn't one-sided. While quantum computing promises to revolutionize AI, AI is proving to be an absolutely essential tool for building quantum computers in the first place. Think of it as AI helping to tame the quantum beast. The biggest challenge in building a quantum computer is that qubits are faulty. They are constantly making errors due to that decoherence we mentioned earlier. The solution is quantum error correction, a complex process of using many physical qubits to create one stable, logical qubit. Detecting and fixing these errors in real time is a massive computational challenge. This is where AI shines. Machine learning models can be trained to recognize the subtle signatures of different errors and apply the correct fix faster and more accurately than any traditional method. It's like having an AI-powered mechanic constantly tuning the quantum engine. AI is also critical for simply operating the hardware. The lasers and microwave pulses used to control qubits need to be calibrated with incredible precision, and these settings can drift over time. I can automate this painstaking process, constantly monitoring and retuning the hardware to keep the quantum computer stable and reliable. So what will this new quantum AI synergy actually do for us? The applications could reshape our world. Take medicine and drug discovery. Designing a new drug means simulating how molecules behave, a quantum mechanical problem that classical computers are terrible at. But a quantum computer can simulate these molecular interactions with perfect accuracy. Quantum AI could rapidly test millions of potential drug candidates to find the one that perfectly targets a disease like Alzheimer's or cancer, slashing the time it takes to develop new medicines. It could also lead to truly personalized medicine, analyzing your unique genetic code to design a treatment tailored specifically for you. In finance, quantum AI could revolutionize risk analysis and portfolio optimization. By analyzing countless market variables simultaneously, it could build investment strategies far more robust and profitable than anything we have today. It could also spot complex patterns of financial fraud in real time across billions of transactions. Then there's materials science. We could use quantum AI to design new materials atom by atom. Imagine creating a new catalyst that efficiently scrubs carbon dioxide from the atmosphere, or a new material that enables room temperature superconductors, or a battery that is 10 times more efficient. These are the kinds of breakthroughs that could solve some of humanity's biggest challenges. But with great power comes great risk. The power of quantum computers poses a direct threat to our modern digital world. Most of the encryption that protects our online banking, private messages, and government secrets relies on the fact that it's too hard for classical computers to factor large numbers. But a powerful quantum computer could break this encryption with ease. This has sparked a race to develop new, quantum-resistant encryption methods. On the flip side, quantum mechanics also offers a solution called quantum key distribution, which uses the laws of physics to create theoretically unhackable communication channels. Of course, we are still in the early days. The road to a full-scale, fault-tolerant quantum computer is long and filled with immense engineering challenges. The biggest one remains qubit stability, and the need to scale up from a few hundred noisy qubits to millions of stable ones. We also have to be mindful of the ethical implications. If quantum AI is trained on biased data, it could amplify that bias on a massive scale. And the immense power of this technology could become concentrated in the hands of a few companies or nations, creating new geopolitical divides. For now, We are in what's called the noisy intermediate scale quantum, or NISQ era. Today's devices are too small and error-prone for the most famous quantum algorithms, but they might be powerful enough to provide a quantum advantage on specific, practical problems in the near future. The most likely path forward is a hybrid one, where quantum processors act as specialized coprocessors, working in tandem with classical computers to tackle the hardest parts of a problem. The synergy between AI and quantum computing is a catalyst for a new age of computation. We are at the very beginning of a journey to harness the fundamental laws of the universe to power the intelligent systems of tomorrow. The challenges are significant, but the potential to revolutionize medicine, science, and society is truly profound. We are charting a new frontier that will undoubtedly reshape our world in ways we are only just beginning to imagine.